Ranking systems at companies like Meta or Google face a fundamental tension. They need to score thousands of candidate items against a user's preferences in milliseconds, drawing on years of interaction history. And they need to do this billions of times a day within tight compute budgets. So when the transformer revolution swept through language modeling, it was natural for the recommendations community to try adapting those same architectures. But the authors of SlimPer argue that this borrowing has a hidden flaw, and they propose a fundamentally different way to think about the problem. Here's the core mismatch they identify. Large language models justify their expensive intermediate representations because every single token position produces a prediction during training. If you're processing a 1,000-token sequence, you're getting 1,000 supervision signals, so maintaining rich per-token hidden states across every layer pays for itself. Recommendation is completely different. For each user item pair, you produce just a handful of relevant scores. Maybe click probability, share probability, comment probability. That's it. So when you take a transformer and apply it to a user history of 10,000 events, you're paying a massive memory and compute tax to maintain full token-level representations that never actually get supervised at the token level. It's like renting a warehouse to store inventory when you only ever ship one box. The field has been living with an awkward trade-off. Either aggressively compress those intermediate representations and lose information, or keep them large and burn compute. Prior approaches tried to work around this in various ways. Models like Douyin and SassRec applied attention over user history for intent modeling. HSTU introduced request-only optimization, meaning user-side computation is done once per user and shared across all the candidate items being ranked for that user, which is a big win because you might rank hundreds of items for the same person. Other work like OneTrans and RankMixer tried to unify sparse features, dense features, and sequences under one transformer backbone. But all of these still carry the same architectural DNA. They propagate token-level intermediate tensors through depth, and the quadratic cost of attention over long histories limits how much user behavior you can actually consume. SlimPer's key move is to reframe ranking as iterative refinement of a small, fixed-size knowledge base. Think of the knowledge base as a compact scratch pad. In their experiments, just 64 slots of 256 dimensions. That represents the model's current understanding of this specific user item pair. It's initialized from the item side features. Then each layer does 3 steps: select, match, and refine. In the select step, the current knowledge base generates query vectors, and those queries attend over the full set of raw user-side tokens, which can number in the thousands or tens of thousands. Importantly, the queries condition on what's already in the knowledge base. So the model is asking targeted questions like, given what I know so far, what else should I look at in this user's history? In the match step, the retrieved evidence is compared through explicit dot products against a set of learned templates, producing relevant scores. In the refine step, those scores get normalized and pass through a small MLP that updates the knowledge base for the next layer. The magic here is that the knowledge base stays the same fixed size at every layer, regardless of how long the user history is. Yet at every single layer, the model has direct access to all the raw user tokens. This decouples model depth from sequence length. You can stack 10 layers over a 10,000 event history without the memory blowing up because you're never propagating a 10,000-sized intermediate tensor through the network. The per-layer cost is linear in the number of input tokens rather than quadratic. And the memory footprint is dictated by the tiny knowledge base rather than by history length. The authors extend request-only optimization to every user-side feature modality, not just sequences. So, sparse user features, dense user features, and sequence features are all computed once per user and shared across every candidate item in the same request. During inference, when you might be scoring hundreds of candidates for one user, this amortizes beautifully. They contrast their design with what they call the transformer's interaction capacity problem. Transformers spend most of their O of n squared compute on user-token-to-user token pairwise interactions, but those interactions don't directly serve the actual task, which is scoring user item relevance. SlimPer redirects that capacity toward k times n interactions per layer that are all knowledge-based to token, meaning every computation is doing relevance work. There's a nice information theoretic argument tucked into the paper. You might worry that squeezing everything through a 64-slot bottleneck loses information. But the target you're predicting is only a handful of scalar probabilities per pair, so the mutual information between input and output is bounded by maybe a few dozen bits. The knowledge base has vastly more capacity than that, and because each layer cross-attends into the raw inputs rather than only the compressed representation from the previous layer, the model can recover any information that earlier layers happen to drop. This breaks the usual data processing inequality argument against bottlenecks. Their attention heat maps confirm the intuition. Lower layers attend broadly across thousands of past events, while upper layers narrow their focus to the most recent few hundred, showing the iterative refinement in action. The empirical results are substantial. On Instagram Reels and Feed, at matched sequence lengths, SlimPer improves normalized entropy by around 0.5%, while also delivering roughly 11 to 12% higher throughput and 9 to 18% lower memory. When they scale up to 5,000 or 4,000 events, the gains grow to nearly 1% any improvement on some tasks, which is a huge margin in this domain where 0.03% is considered meaningful. In flop terms, SlimPer uses about 8 times fewer floating point operations than the baseline at 2,000 events, and the ratio grows to 25 times fewer at 6,000 events. The live A/B test delivered engagement gains roughly 10 times larger than a typical statistically significant launch, and it's now serving full traffic across multiple meta surfaces, with newer variants scaling to over 10,000 events per user. The limitations are worth being honest about. The comparison is against Meta's production baseline, which is a hybrid of HSTU for sequences and Wukong for fixed-size features, rather than a direct head-to-head with recent unified transformer architectures like OneTrans or RankMixer. The authors argue the hybrid is actually a stronger comparison point than any single unified architecture, and their complexity analysis is general, but a direct empirical bake-off would be more definitive. Everything is on internal Instagram data, so reproducibility outside Meta is limited to re-implementing the architecture on your own data. And while the design is elegant, some choices like the exact size of the knowledge base or the number of query slots are empirically tuned rather than principled. Now let's walk through some questions you might have after hearing all of this. First, why does maintaining a fixed-size knowledge base not lose information when transformers seem to need full token-level representations? The key insight is that transformers only need to compress information within a layer because the next layer only sees the compressed output. In SlimPer, every layer reaches back into the raw input tokens directly, so if one layer's refinement missed something important, later layers can recover it. The knowledge base is more like working memory during a research task, where you keep notes but always have the source documents on hand, rather than a summary you pass down a chain where each person only sees the previous summary. Second, what's actually happening in the matching step with these templates, and why is that different from standard attention? Standard attention aggregates values weighted by query key similarity, producing a soft mixture of evidence. SlimPer does that too in the selection step, but then it adds an explicit second step where the retrieved evidence is dotted against a separate set of learned template vectors. You can think of the templates as capturing different facets of what makes a user item pair relevant, like topical match, recency, engagement style. The explicit dot products produce interpretable relevance scores along each facet, which then drive the knowledge base update. It's a more structured relevance computation than just letting a big MLP figure it out. Third, if the knowledge base is initialized from item-side features and refined by pulling from user-side features, does that mean SlimPer is fundamentally an item-centric architecture? Yes, that's the right framing, and it's actually a deliberate inductive bias for ranking. The task is to score each candidate item against the user, so starting from the item and iteratively pulling in relevant user evidence mirrors the actual question the model is trying to answer. It's also what makes request-only optimization so effective, because the user-side tokens can be computed once and reused as the shared evidence pool that every different item initialized knowledge base queries into. For large-scale recommendation systems serving hundreds of millions of users, the practical implications here are significant. The request-only optimization pattern extended across all user modalities is directly applicable to any two-sided ranking system where you fan out one user against many candidates. If your current ranker recomputes user representations per candidate, you're leaving substantial GPU savings on the table. Beyond that, The decoupling of depth from sequence length opens up a specific opportunity. You can finally consume raw lifetime user history, tens of thousands of fine-grained events without the quadratic wall that has forced teams into lossy compression, retrieval-based summarization, or offline pre-aggregation like Twin v2 or DV365. That means fresher signals, better cold start recovery when interests shift, and no more maintaining a separate offline aggregation pipeline just to keep serving costs sane. The architecture also fits naturally into early-stage retrieval and mid-stage ranking. Not just final stage ranking, because the item initialized knowledge base pattern amortizes even better when you're scoring thousands of candidates. And the intrinsic interpretability, where attention weights directly attribute a prediction to specific past user events, is genuinely valuable for the debugging, auditing, and creator-facing explanation surfaces that are increasingly required in production recommender systems. The core lesson is that borrowing architectures wholesale from language modeling leaves real efficiency and quality on the table. And designing around the actual computational shape of ranking, one prediction per pair with massive candidate fanout unlocks scaling that transformers were never going to give you.